Welcome to the 9th lecture in general topology. The topics that we'll explore in this lecture include additional properties of the digital line, relations on sets, partially ordered sets, simply ordered sets, and an introduction to the order topology.
Okay, so we'll start by looking at some of the exercises from the previous lecture. So first, we'll show that the collection script B sub E, consisting of the basis elements for the even integers, is an open cover but is not a basis for the digital line. So proof. Clearly, the collection script B sub E is a collection of open sets Now let m and m plus 2 be two even integers. Then the basis element B sub m is the 3-point set m minus 1, m plus 1. And the basis element B sub m plus 2 is the 3-point set m plus 1, m plus 2, m plus 3. So notice that the intersection of these two basis elements is the singleton set containing the odd integer m plus 1. And so for every pair of consecutive even integers, both even integers and the odd integer between them are in the union of the basis elements B sub m and B sub m plus 2. In other words, we will always have an overlap between two basis elements when we take a union. And so the union of all such basis elements, that is the basis elements for the even integers, is the entire set of integers. And hence the collection script B sub E, which contains precisely these elements, is an open cover for the set of integers, or for the digital line. However, this collection is not a basis for the digital line, since for the odd integer, m plus 1, this odd integer, m plus 1, is in the intersection of B sub m with B sub m plus 2, but there does not exist an element b in the collection script B sub E such that this odd integer is in that basis element, which is a subset of the intersection of B sub m and B sub m plus 2. Okay, so next we will show that the digital line is T0 or Kolmogorov. Now recall from the previous lecture we demonstrated that not every singleton set is closed. In particular, the singleton sets containing the odd integers are open but not closed. And so the digital line is not T1 and therefore is also not T2. And so we will now show that the digital line is T0, and this is the strongest separation condition satisfied by the digital line. So proof. Consider the consecutive integers m and m plus 1. Notice that one of the integers, m and m plus 1, is even, while the other is odd. Without loss of generality, we may assume that the integer m is odd. Then the basis element b sub m, which is the singleton containing the integer m, is an open neighborhood of the integer m, such that the integer m plus 1 is not in this neighborhood. However, the smallest open neighborhood containing the point or the integer m plus 1 is the basis element b sub m plus 1, which is the 3-point set containing the integers m, m plus 1, and m plus 2. And clearly, the integer m is in this basis element. So now consider two integers, m and m plus 2, that are separated by a given integer. Notice that these integers are either both odd or both even. Suppose that both are odd. Then the basis element b sub m, which is the singleton containing m, is an open neighborhood of the integer m, such that the integer m plus 2 is not in this neighborhood, and the basis element b sub m plus 2, which is the singleton containing the integer m plus 2, is an open neighborhood of the integer m plus 2, such that the integer m is not in this neighborhood. So now suppose that both integers are even. Then the basis element b sub m, which is the 3-point set containing the integers m minus 1, m, and m plus 1, is an open neighborhood of the integer m, such that the integer m plus 2 is not in this neighborhood, and the basis element b sub m plus 2, which is the 3-point set, m plus 1, m plus 2, and m plus 3, is an open neighborhood of the point or integer m plus 2 such that the integer m is not in this neighborhood. Now, more generally, if m and n are two integers where the absolute value of the difference of those integers is greater than or equal to 2, then the basis element, b sub m, is an open neighborhood of the point m such that the integer n is not in this neighborhood, and the basis element, b sub n, is an open neighborhood of the integer n such that the integer m is not in this neighborhood. And so for every distinct pair of integers, m and n, there exists an open neighborhood for at least one not containing the other, and hence the digital line is T0 or Kolmogorov. So now we can summarize the topological invariants that we have studied so far for the digital line. So we look at the number of isolated points, we look at connectedness, the strongest separation condition satisfied, and at the countability condition. And this is not necessarily the strongest, but this is the only one we've studied so far. The separation condition satisfied by the digital line is that it is separable as it contains a countable dense subset. Namely the odd integers. The number of isolated points in the digital line is the cardinality of the set of odd integers, which is Aleph null. It is countably infinite. The digital line is connected. And the strongest separation condition satisfied is the T0 or Kolmogorov condition. Now, as the digital line is connected, the only sets that are both open and closed are the empty set and the entire set. So we now consider whether there exists subsets that are neither open nor closed. And we'll start by looking at a condition that must be satisfied by an open set containing an even integer. So let A be a subset of the digital line, and let M be an element in the set A where the integer M is even. If the set A is open, then the two consecutive odd integers, m minus 1 and m plus 1, are in the set A. So proof: suppose that the set A is open, and let the element m be a set or an element in the set A where m is even. Then, as the set A is open, there exists a basis element containing the point m, which, as it is even, the smallest such basis element is the basis element b sub m, which is the 3-point set, m minus 1, m plus 1, in the basis, script b, such that the point m is in this basis element, which is a subset of the given open set A. But then the consecutive odd integers m minus 1 and m plus 1 are in the set A. This is a contradiction if either the odd integer m minus 1 is not in the set A, or the odd integer m plus 1 is not in the set A. And so the set A must contain both odd integers m minus 1 and m plus 1. In other words, if we have a subset in the digital line that contains an even integer, and if it does not contain both of the consecutive odd integers about that even integer, then that set is not open. And so we will now look at an example. Let m and m plus 1 be two consecutive integers. Then the 2-point set containing these consecutive integers is neither open nor closed. So proof: notice that one of the integers, m and m plus 1, must be even. And so the 2-point set, m plus 1, does not contain both consecutive odd integers centered about the given even integer. And hence the 2-point set, m plus 1, is not open Now, without loss of generality, we may assume that the integer m is even, then the closure of the 2-point set containing the integers m and m plus 1 is the union of the closure of the singleton containing m with the closure of the singleton containing m plus 1. As the integer m is even, the closure of the singleton containing that is the singleton containing that even integer. And as the integer m plus 1 is odd, the closure of the singleton containing that odd integer is the 3-point set containing m plus 1, and m plus 2. And so this union is the 3-point set, m plus 1, m plus 2. And so as the closure of the set is not equal to the set, we have that the 2-point set m plus 1 is not closed, and hence the 2-point set is neither open nor closed.